Good afternoon, everyone, and welcome to the RISA Connection webinar series. In today's webinar, Efficient Design of HSS Connections, presented by the Steel Tube Institute and RISA. My name is Ben Follett, and I'll be one of your presenters today alongside Kim Olson from the Steel Tube Institute. Before we jump into things, just a little bit of housekeeping. If you're new to the Zoom webinar settings, when you log in, you should have received some audio options to choose whether to use the phone call audio or the computer audio. Both work just fine. You can either dial in using the phone number there and the meeting ID, and you can also use your computer audio if you just choose to use the headset or the speakers on your computer. All attendees will be muted, so we won't have any live questions, but you can use the Q&A button on your navigation tab there to enter any question you'd like, and we will have some engineers that will be answering questions throughout the presentation, as well as we'll be taking a few questions or answering a few questions live at the end of our presentation. One other thing to note, we will be sending the PDH credits for the webinar for all the people that registered individually. Those will be sent out after the webinar. We'll also be posting the webinar and posting the questions and answers, as well as some of the slides from the webinar after the webinar. So if you have any other questions after the webinar, you can certainly email us directly at info@risa.com. But with that, I'd like to turn the presentation over to Kim, who can introduce herself a little bit more and begin the webinar. Kim?
Thank you. I just got to get my slide sharing. Ben, you seeing that okay?
We are not yet seeing anything.
How about now?
Now we are.
Perfect. All right. Good afternoon, good morning to those of you in the West. My name is Kim Olson. I am a structural engineer with Force Consulting. Here at Force, we do the technical consulting for the Steel Tube Institute. And so we do a lot of presentations and create technical content for them, living in the world of all things HSS. I'm going to take about 20 minutes here to guide you through some of my favorite topics when it comes to HSS connections. So these are the things that I get the most questions about, or kind of my little pet peeves. So bear with me as I jump on my soapbox for the next 20 minutes and hopefully guide you through and give you some information that you can use in your everyday work. All right, so starting off with a little question here, true or false. I know we're in a webinar format, so it's a little bit more difficult, but you can play along with your coworkers that may be sitting next to you. But true or false, HSS structures in general are more expensive than those made up primarily of wide flange sections. And right off the bat, I'm going to tell you that this is a trick question. There's not really a right or wrong answer to it, which is why I love putting it up here. So when we talk about structures in general, so a completed structure, there are those two major components to that, the material and the fabrication costs. Material cost per pound of HSS is different than material cost per pound of wide flange section, obviously. So if I'm comparing the cost per pound, that's almost like comparing apples to oranges. However, if I compare the cost of a column that has 100 kip capacity made out of HSS sections versus the cost of a column made out of an open section that also has 100 kip capacity, an HSS is always going to be less expensive. It's a more efficient use of that material, of that steel, because obviously it doesn't have that weak axis member. However, if you look at per pound, a wide flange is going to be less expensive. So really, when we talk about the material costs of HSS, we need to think about the capacity of the member, not just looking at the member on a per pound basis. And like I said, most often you'll find that the HSS section is going to be less expensive. But then there's also that other component that we're going to focus on today, and that's the fabrication or the connections. These are a little bit harder to quantify. Different fabricators have different thoughts on HSS. Some of them are set up to bolt everything in their shop, like that's their beam lines are set up to bolt, and so therefore they're less, I would say, HSS friendly than those that are set up to weld. Likewise, if they don't have a lot of experience with HSS, they may price the job that has a lot of HSS a little bit higher than someone that is familiar with HSS and knows how to work with it. So the fabrication component is really what I want to talk a lot about today when it comes to these connections, because there definitely are some better ways of specifying connections when it comes to HSS so that we can try and keep that total cost of the material and the fabrication down. All right, so starting with shear connections, these are obviously the most common connections we deal with on many of our jobs. These are all listed from least to most expensive. And so first off, you can see here the single plate connection. Very economical connection here. We're connecting to the face of the HSS wall with a single plate. Can be bolted or welded to the beam, but most often it's bolted for ease of erection. And then it's welded to the face of the tube. So it doesn't get any more economical than this, and this is probably a good connection to have on your drawings for your typical shear connection. If we're needing a little bit more capacity, we can then go to the next one over, which is the WT connection, where we're actually using a WT section to connect to the HSS wall there. The reason why we get a little bit more capacity out of this is you can see that WT is actually delivering the load a little bit closer to the sidewalls. So if you think of the base of the HSS section as a thin plate that then has to span to the sidewalls to deliver the load, you can see why being closer to the sidewalls will give us a little bit more capacity in that connection. Next, looking at the double angle connection here, this is going to give us a little bit more, even more capacity. Again, we're delivering that load to those sidewalls, plus we get the double angle connection in the beam web to give us a little bit more capacity if we need that. I would just caution you here with the double angles, we need to pay attention to the geometry. You can see that I've noted this column that I'm connecting to is 8 inches wide. I would say that's probably a minimum that you want to use when you're connecting using double angles, just because we need to have, for pure geometric reasons, we need to have a face that is wide enough to be able to fit those double angles on it. So if you're using squares, I would start at 8 by 8s and go up. If you're using rectangular sections, start with an 8-inch face, and obviously higher than that or longer than that is fine as well. And then lastly, the last connection we're going to talk quickly about is the through plate connection. This is my nemesis here. A through plate connection is when it looks a lot like a single plate connection that we talked about first, but we're actually slotting the tube and passing the plate all the way through. You get more capacity out of this guy because you can see that I'm actually engaging two walls here. But you can imagine the cost implications to this, where we're asking the fabricator to not connect to the face of the HSS, but to create a nice, neat slot through two of the walls of this HSS. They need to line up, and then we obviously need to fish this plate through there and then create the welds for that through plate connection. So it can be a bit more expensive. Before I go to the next slide, I just want to point out that although we're talking about rectangular sections here, a couple of these can be used for round sections. If we're connecting to kind of a circular section, we wouldn't be able to use the double angle, obviously, or the WT, but the single plate or the through plate connection can be made to those circular sections. Talking a little bit more about this through plate connection is that there has been some research done in the past that has found that this connection can be 4 times more expensive to specify a through plate than just a simple shear plate connection that is welded to the face of the tube. It's always going to be more efficient for you as a designer when we're thinking about the total cost of our project to increase your wall thickness. So go from a 3/16 inch wall to a 1/4 inch wall if that's going to allow us to connect to the face of the tube rather than having to slot through the tube. That's always going to be more economical than using a through plate connection. And you also need to watch your weld symbols. I'm not joking that I pulled this detail, I redrew it so that nobody could tell where it came from, but I pulled this drawing from a fabricator that sent me their job, and you can see that if we've actually got this specified as our typical connection. We've got through plates going in 2 different directions. So the fabricator literally has to cut the tube in half to be able to fit this kind of crucifix type or shaped plate on the inside, and then we're asking for the weld to be made on the inside of the tube as well. It just doesn't make a lot of sense. So we need to pay a lot of attention if we are going to specify these through plate connections so that we're not incurring an incredible amount of costs on the fabricators and then having to weld this column back together after we've placed all these plates on the inside. I'm not saying never specify through plates. I just don't want them specified as our typical connections. Obviously, there's definitely a place for it. So if I'm using this type of connection as a drag, an axial drag where I'm trying to pass axial load from one side of a column to another, there's really no more efficient connection than a through plate connection. Absolutely specify that. Obviously, if you're a connection designer and you don't have a lot of control over what the EOR has specified for the thickness of the material, then you might end up having to specify a through plate connection. My point here being today is that we just don't want to specify it as our typical standard connection, you know, that detail that we pass from job to job to job when we're setting up a new job. We don't want this specified as our typical connection. Hopping over to real quick to look at moment connections. First, I should say that these 4 connections that we're going to look at today have about the same capacities. These are non-seismic pre-qualified connections. So this would be something you would use for wind or low seismic RF3 type thing. And these also aren't in order of cost, although I will talk about the cost in the end or at the last slide here. So first would be a PJP option where we're directly connecting a wide flange beam to an HSS column. We're connecting to the face of the tube with a PJP weld. It's not something that I think a lot of us as engineers automatically go to this CJP option. I know I've been guilty of that in the past, but you really are going to save a lot of money if you have the capacity to be able to use a PJP rather than going to a CJP. Take note that when we're actually connecting to the face of the tube, as in these 2 connections, we need to use a 5/8 inch wall in order to get this a similar capacity. So I've got a little bit thicker wall in this material than you'll see in this next slide. So this next slide uses a couple of different scenarios here for connection. These are through plates and cutout plate options. So similar to the through plate option that we just looked at for a shear connection, I am interrupting the column in order to pass these top and bottom flange plates through. So the column gets cut into actually 3 pieces. We've got a bottom piece here, we've got a plate that is going to pass through, and typically you would see the same connection on the other side. I just made it one-sided just for illustration purposes here, but we've got this bottom flange plate, and then we've got to sandwich in back this middle section here, and then we've got a top flange plate. If this is a connection that you're using, you can see this can be a convenient place to splice. So if you wanted to change column sizes above, you can see that splice plate there, and that all can get bolted together. But we're interrupting the column here. On the plus side, though, I can get away with it using a thinner column or a thinner wall. As you can see, I've got a 3/8 inch wall here for this guy. Similar to a through plate option, although not quite as expensive, is a cutout plate option that you see on the right-hand side. So this guy looks similar, although the nice thing about it is we're actually wrapping the plates around the column. So I'm not having to interrupt the column. I'm not stopping, starting, and having to do those expensive splices. I'm wrapping a top flange and a bottom flange plate around it and welding it to the face of the column. Again, I can get away with a 3/8 inch column for this option as well. So giving you an idea of the relative costs, this is very difficult to quantify based on the region and the type of fabricator that you're talking about. And so what I did is I surveyed about 5 or 6 fabricators, and then I averaged their costs, and I set the PJP weld as being the least expensive. I set that as 1 and went up from there. So you can see these costs that I'm giving you here definitely include the material costs. So although the PJP and the CJP weld material is thicker and therefore more expensive, you're still going to end up with the PJP weld being the least amount of cost here. CJP weld, although it shows that it's, you know, kind of in that middle range, one thing that's missing out of here that you would have to have for the CJP weld would be the cost of the inspection. So we need to take care and remember that as well. The through plate being the most expensive, but also the strongest connection of the four, and then the cutout plate connection being the second least expensive option there. So that kind of gives you relatively some options there for remote connections and their costs. Jumping forward, if we're connecting tubes to tubes together, so like in truss type connections, there are two different ways that we classify them. Typically, matched connections would be if I'm connecting a 6x6 branch member to a 6x6 cord member, or it could be a 6x6 beam to a 6x6 column, where those dimensions are equal. Obviously, architecturally, this is what most architects are going to prefer. If they're specifying kind of the section that they would like to see, they're probably going to specify something like this. But I want us as engineers to be a little bit more informed and be able to talk to them about the cost implications of this. A step connection would be where I'm able to land the member, the branch member, on the flat of the tube. The flat being the overall width of the tube, the B dimension, minus about 4T. So we average the corner radius to be about 2 times the thickness of the tube. So if we can, you can see that if we can land it on the cord member on the flat, then we can get away with a fillet weld, which is going to be much more efficient and much less expensive than the flare bevel groove weld that we are ending up with on the sides of the match type connection. And you can see that here. You can imagine, because the radius of the tube varies depending on the thickness of the tube, as we get to thicker and thicker tubes, this radius is going to be bigger and bigger. As we try and land an equal size section on that curved area, you can see that we no longer can get a pre-qualified connection. So they're going to have to do something in order to get a pre-qualified connection. And these are the three options here. I hope you see that can be some significant cost involved in this. Tube profiling, where they actually don't cut the tube straight. They actually have to cut it so that those side walls are longer than maybe the walls that are running along the flat of the tube. Weld backing is something they can also employ, or steel backing. All of them involve some significant costs. And if we can talk to our architects about making an informed decision, do we really need to have a match connections, or can we get away with a step connection? This is the Skydance Bridge over I-40 in Oklahoma City. I did a presentation there once, and me being a dorky HSS engineer decided to pull over and take a closer look at these connections. And sure enough, because just like what I was preaching, these connections are step connections, and you can probably see that here. So this is a perfect example of this. I'm guessing that architecturally, the architect probably drew these connections to be the same size, so they're nice and flush and pretty. But let's be honest, we're driving at 80 miles an hour underneath these things. Could we really tell that all of the connections are flush? No. So they probably saved a decent amount of money by making those branch sections a little bit smaller in order to employ a fillet weld all around them and save some money on the fabrication costs of this bridge. Likewise, minimum weight of a truss does not equal least cost. As I started out with, the fabrication costs can weigh heavily into a finished structure. So if we're looking at these three options on the right-hand side and talking to our architect through some preliminary design, a Howe truss or a Pratt truss is going to be more expensive. Yes, the cord members are going to be lighter, but there's going to be more connections that have to be made, more joints than in a Warren truss, and therefore a Warren truss, although it may have a heavier weight of tonnage of the steel, the total overall cost is going to be less. We always want to size our welds for what we need. So unless we absolutely need to employ something like plastic stress redistribution, where we've got moment loads or need to design for the upper limit of the weld size, let's always have or size the welds ourselves, or have the connection designer size for exactly what we need. So we're not over designing those connections that hopefully can be made using an economical fillet weld. A gap connection is always going to be less expensive than an overlap connection, although we do get more strength and stiffness out of that overlap connection. A gap connection allows the fabricator to kind of tack these pieces in place before they do the final welding, and that's going to help with the overall cost of fabrication of a truss. I talked about this earlier, but obviously PJP welds are preferred over a CJP weld. CJP welds, if they have to be made without backing, it requires a 6GR welder certification and some special fit up, which is big money. And especially for those of us that don't live in an area like Houston or New Orleans where they do a lot of offshore oil work, a 6GR welder may not even be available. So the fabricators that I talked to first said to go up to a fillet weld size of 1/2 inch, then transition to a PJP, and then obviously if that doesn't work for you, then you can go to a CJP if required. Engineers have always, and I've been guilty of this, put some sizes on their drawings that aren't necessarily produced. Just because section size is in the steel construction manual doesn't mean that it is readily available for you. So we've created this tool that's on the Steel Tube Institute website that helps guide you into what sections are available for you. So it's on the front page of our website. You can pop in the size that you're looking for. In this case, I searched rounds from 6 to 10, and then click search and you'll see results that look like this. Anything in green means that at least one of our members regularly rolls that section. So you're pretty safe in specifying it. Something that's yellow means that our producers have the ability to make it, but they're not regularly rolling it. So unless you need a lot of it and have some time to wait for them to actually make it, I would try and avoid the yellow sections. And then something with a dash means that none of our producers are making it and they don't have the capability to make it, so you definitely want to avoid it. There's a chance that there is some imported material coming into the United States that would meet those sizes, but we have no way of checking on that and telling you where it might be. So it's a bit of a gamble to do that. And then going a step further, if you need to see who actually makes it, you can click on any of those colored cells, and the producers that actually make it are given here. All right, so now to the really exciting stuff. In 3 minutes, I'm going to cover the changes in the code. In 2010, we're used to seeing the charts. They're very nice and easy to follow. However, they're very prescriptive, which is unlike most of the code. There was some repetition to it. It's very unique. None of the other chapters in the specification follow that type of format. And there were always questions about the limits of applicability. What do I do when I'm outside the limits of applicability? So now we're looking at 2016, and it has a new title, Additional Requirements for HSS and Box Section Connections. The introduction to this new Chapter K clearly states that what's in Chapter K needs to be applied in addition to the requirements of Chapter J. And if you flip through, you'll see that a lot of our tables are no longer there. We're treating HSS connections the way we do wide flange connections. We're not given the limit state that's going to control a particular wide flange section. We have to go through and see what exactly is going to control our connection design. And we may do 10 different checks to identify that limit state. We're now going to go through the same process for HSS connections. When it comes to round sections, those are largely unchanged. The tables are mostly still there and still intact. There is a new limit of applicability that we need to pay attention to, and that's if we're connecting close to the end of the members. But when it comes to rectangular sections, most of it is referencing Chapter J. Fundamentally, if you can remember these two screenshots here, if you can remember that when we are connecting to a tube, it's very similar to the limit states that we would check if we're connecting to the web of a wide flange, right? To a tube, we're connecting to a plate that is spanning between sidewalls. When we're connecting to a wide flange on the right, we're connecting to a web member that is spanning to flanges. So we're no longer limited. We don't have the limits of applicability that are kind of constraining our design in theory, but we now are being forced into Chapter J to look at the complete picture of these connections. It's a bit of a leap, and I know it's very difficult if you're first starting out, and so we've created these resources to help you through this. I know you can't read this, it's very small, but what we've done is created these resource limit state tables. So getting closer, you can see here are the pictures that you're used to, right? So we all feel comfortable with that. Text in the black is the 2010 specification. Text in blue is the 2016 specification. So very easily we can see exactly how we can go between the two specifications. If I'm trying to design something in the new specification, here's the formula that I need to use. Here are the variables that I need to substitute to get there. And then lastly, those resources that I just showed you are available on our website. If you go to steeltubeinstitute.org, under Products and HSS, there is a column called HSS Information. You can see that here, AISE 36016. All of those tables are divided up and given here, and you can download those for free. All right. Last thing I wanted to talk about real quickly is the A500 B versus C. I know this is a little bit off topic, but those of you that have gotten into the new specification hopefully have noticed that all of your column tables are based off of A500 grade C. Our producers are very smart people. They don't stock 2 sets of coil. We've been receiving dual grade material for at least 10 to 15 years, and we haven't known it. So we need to go ahead and be specifying A500 grade C for our designs, because that's what we're getting, that's what we're paying for. You're not going to be asked to pay a premium for that. So that's my soapbox in 23 minutes. I went 1 minute over. Sorry, Ben. I'm going to pass this off to you.
Awesome. Thanks very much, Kim. So now, Kim gave us did a great job of giving us a little bit of the background into some of the HSS connection things that the Steel Tube Institute likes to talk about. Obviously, there's a lot of questions that you guys have. I know Kim will be able to answer some of those while I'm presenting. But really now we want to transition to focusing a little bit more on RISA and really how can RISA handle some if not all of the connections that maybe you're looking to specify. And so just to start, available design codes that are available in RISA Connection for HSS considerations. We have the AISC 36016, 10 and 5, both for ASD and LRFD. Also, we have the Canadian codes, both the 14th and the 9th edition. Here's just a kind of a simple list of the HSS connection types that we do include right now. And so most of it is for an HSS column. We're always looking to develop, always looking to add more functionality to RISA Connection and all our programs in RISA. And so one of the things that we always mention to people is that if there's something that you need, if there's something that you want, if there's a connection that you use all the time that you're looking for a software to be able to do, please let us know. We'll add it to our development ticketing system, and we'll the more people that ask us for that, the more requests we get, the more we know that the market needs it, the more that we'll go ahead and be able to add those things. But we'll go ahead and look at a variety of these connections. The last thing I wanted to talk about, though, before we get into kind of a live demo of this, is one of the best things about RISA Connection, if you're not already a RISA user, is its integration with RISA 3D and RISA Floor. And so whether you're starting a project in RISA Floor or starting a project in RISA 3D, you can integrate with RISA Connection. So you don't have to use all 3 products to be able to do this. You can go ahead and integrate really from one or the other and even back and forth. So we'll be able to see a little bit of that process here live. And so I'm going to go ahead and switch to our RISA 3D model. And so I just have a really basic RISA 3D model here that we're showing. Nothing too crazy. We just have a building that we're going to use to, kind of send some information back and forth and really to do our connection design. So we've got some loads already applied. This model was built in RISA Floor and then transferred into RISA 3D, but we have a different number of loads. We've got some seismic loads, so we've got some wind loads, so we have gravity and lateral load all together. Now, the first thing I want to look at here is I want to show and open up the connection rules spreadsheet. So I'm going to open up this spreadsheet here. This is all of the different connection types that exist, both shear, moment, brace, base plate, and truss connections that exist here in RISA. This connection rule spreadsheet in RISA 3D allows us to define those connections on the ends of members here in RISA 3D and then actually transfer that information to RISA Connection. And so we can see here that if I go ahead and close this out and I turn or I enable here my connection rules, I can see some of the different connection rules that we have individually on a different members. And so I've assigned a few different ones. So I've got some column beam shear tab connections. I've got some base plate with vertical brace connections. I've got some diagonal vertical brace connections. We've got some different direct weld and column flange plate moment connections. And so just a variety of different connections that are assigned on the model. And so the last thing I want to mention here before we go ahead and transfer this information to RISA connection is I'm going to go into my materials spreadsheet. So one of the things that Kim may have mentioned, and one of the things that's kind of big in the HSS industry, is the use of A1085. And so for this example, I'm going to use 1085. And so if you're not familiar with A1085, really it allows us two main things, in my opinion at least. First is we're allowed a 50 KSI minimum yield stress for all HSS shapes. That's one of the things for A1085. The other is allowing us to use the full nominal weld thickness in the calculation. So no more of that 0.93 kind of factor that you were used to using for other materials here, so other A500 materials, for instance. So that gives you, because the tolerance is tighter on those HSS shapes, we have the ability to go ahead and use that full nominal thickness, which obviously gives us better strength and so on and so forth. And so I've got this model already run. I've got some analysis results. What I'm going to do here is I'm going to use the director here, and this director is what we use to transfer information between programs. I'm going to jump here into RISA Connection. And so with RISA Connection, I can go ahead and open then, I can go ahead and open RISA Connection, and we can go ahead and look at exactly what we're looking at. And so in this case, I've got my RISA Connection model. I've got my groupings of members, and so we're seeing then the different groups of different members here. And so, for instance, we can see that everything from RISA 3D is put together. And so the first thing we need to do before we go ahead and do anything is we need to solve the entire project. And so I'm going to go ahead and click this Solve button to solve everything. And so when we solve the project, we get some that are just going to maybe pass right off the bat, maybe because we have our settings correct, some that are going to fail. And let's go ahead and evaluate some of these different HSS tube connections as we see them. And so the first one I'm going to jump into here is the direct weld moment connection. And so if I click on the direct weld group, I'm into the individual various connections of that direct weld group. And so one of the really nice things about RISA Connection is going into one of the individual connections, we can see the really nice interface that it offers you. So really ability to kind of look at this connection here in 3D, just kind of zoom around it, look at different views, turn on and off certain things. The 3D view is really nice, but I'm really interested in the 2D views. The 2D views, I think, give a lot of really great information, and really they come down to looking at those views that, that we're almost like putting connection details on our drawings. And so with this, we can go ahead and look at our reports, and we can see just kind of the various information that were provided here in RISA Connection. And so like if I go ahead and expand our HSS limitations, for instance, we can see then just the basic limitations that, that we're using here. And so just some of the basic information. So these limitations are always available to us. One thing that I want to make note of here, and we can go ahead and look at it. We can look at it using maybe one of the other connection types is, if we ever get a connection failure, if we ever see a failure in a connection that has a unity check below 1, what that means then is that there's not a specific unity check or a limit state that's failing. So we don't have maybe a plate block shear problem, but what we have is a limitation, an HSS limitation. And so typically what that means is that we've got a problem with maybe the number of bolts that we have. So like if I, for instance, go ahead and click on our beam bolts here, maybe if I change that to 4, and then I resolve this particular connection, we can see here that we have a unity check that's still under 1, but and it's because our issue is not an issue with any of our limit states, but it's an issue with our kind of our constructability of our particular connection. And so in this case, we can see here that we actually have a failure in our geometric restrictions. Basically, we have a minimum edge distance failure. Essentially, we've got the member passing, or the plate and the bolts passing through that particular member. And so that's where we run into our issues. So the next thing that we can go ahead and look at is going ahead and taking a look at the vertical brace connections. So I'm going to go back to kind of our grouping here, and I'm going to click on our vertical brace connections. Now our vertical brace connections are kind of similar. These base plate vertical brace connections are similar to our regular vertical brace connections. So similar kind of looking at or information that we provide. So if I go ahead and look at the front view, the left side view here, we can see that any of these values that are available to us in the dimensions. So if I select on one, let's just say I click on this 10-inch value here, that's actually the size or the length of that particular gusset plate. And so I can go ahead and manipulate that size here just by clicking on that and changing it. Now we can also see when I make changes, obviously things in this case start to update. So we can see denoted in red here, that's the Whitmore section. And so when I change the size of our gusset plate there, we actually now have an issue because it's in red. We have a failure in our Whitmore section, or essentially our Whitmore section is outside of our gusset plate. And so maybe I actually want to go back to that 10 inches there, and you know we've now got this our Whitmore section that's green, and it's coming back inside the gusset plate there. Let's go ahead and jump into, I'm going to jump into one of the diagonal vertical brace connections. So let's get rid of the base plate one and check out, so let's go back to our connection here and into the diagonal vertical brace connection. And so clicking on one of the diagonal vertical brace connection, we can see here that we actually have a failure. But again, we have a failure with a unity check less than 1. And so the question is, we probably have an issue with basically constructability. And so looking at the 2D view here, we don't really see anything, but looking at the 3D view, we can see very plainly that our issue actually is with our plates. And so if I go ahead and click on one of the plates here, we can see that we have this constructability issue. We can go ahead and very easily go ahead and change our plate size. So if I change this plate size maybe down to a 3 by 2.5 by 5 here, and I can do the same thing just by clicking on that plate. So really easily being able to navigate through things, we can see that we can make that change. Now if I go ahead and again solve the connection, we obviously see that that has now passed. Now let's go ahead and look at a few of the reports. One of the nice things about RISA Connection and its reports is that when you get a more complex connection like this one where you have a bunch of components, so we've got the general part of the connection, we've got the beam, we've got the bottom brace, we could even have a top brace on top of this, so we have all these different types of stuff. We can actually look at the different tabs to see the different parts of the connection. Additionally, one of the things I did want to mention here is that we do have, RISA 3D is sending all of the load combinations from the RISA that you ran in RISA 3D, and in our RISA 3D model you can actually specify, hey, I want to run these load combinations for my RISA 3D model, but I want to run these load combinations for my connection design. And so all of those load combinations then would come over into RISA Connection. Now, by default, it's going to go ahead and choose the kind of worst case enveloped one. In this case, it's load combination 16. But you can go ahead and evaluate other load combinations. So you could just kind of flip through this and we could see then the loading criteria updating. Now, obviously the loading is grayed out because it's coming over from that RISA 3D model. But we could go ahead and do some different things if we want to change this load to custom, or a little bit later here, we'll go ahead and see how we can detach the model from our RISA 3D model so that we can have full control over everything in RISA Connection. Now, the other thing that we can do is once we go ahead and let's say that we've gotten to the point, I know that there's some of are still failing, and we're going to get back to those in just a second, but once we go ahead and maybe finish designing the model, finish designing what we want to design, we can go ahead and actually send this information back into RISA 3D. And so let's go ahead and do that really quick. So I'm going to go ahead up here on our toolbar here, and I'm going to choose to export to 3D. And so if I choose the export button, that information now in our connection design results is populated. So we populate our connection design results here, and we can go ahead and see that some of them are passing. Now some are failing. Some are failing because we have a limit state failure. Others are failing because we have some geometric restrictions at that particular location. And so we can go ahead and see that here in that spreadsheet, or if we wanted to, we can go ahead and actually look at the results here in our model. And so we can see very plainly, okay, here's what passes, here's what fails, here's the unity check here. So really, if you want to kind of integrate this back and forth with each other, you can really take this, this process and do a full kind of round trip integration, both with RISA 3D and RISA Floor with RISA Connection. Now let's go ahead back really quickly into RISA Connection. So I'm going to just pop back here into RISA Connection and read our file again. Now we had, I'll just solve the project really quickly again. So we didn't change anything, but one of the things that I do want to spend a little bit of time looking at is I want to look at this column beams flange plate moment connection. So we have other connections that, that we're not going to spend a lot of time on. So for instance, the shear tab connection, Kim talked a little bit about that, but I do want to go ahead and look at this column beam flange moment connection. And so I'm going to go ahead and pick one of the connections here. So I'm just going to choose this particular connection. And so we can look at it right away. We can see that we have some failure, and the first failure here is some constructability issues, right? And so I'm going to go ahead and look at a top view here, and I can go ahead and change the size of this plate. So I'm going to change the size of this plate from 8 inches to 6.5 inches. And so like you can see, we can anything we grab here, any dimension or any plate or whatever we want to change, we can just grab that and change that in the connection properties. Now if I go back to my reports, we can, and I run this connection again, we can see that that solves our constructability issue, but that doesn't solve our issue that we're having with plate local yielding and also flange plate weld strength. So we've got some other issues that we're needing to deal with. And so if I look at our flange plate weld strength here, we can see here that our standard kind of equation for weld strength, this is a fillet weld. So if I look down here at our welds, we can see we have this fillet weld, we have this fillet weld of a certain size. And so really, I've done some playing with this already to try to change the weld strength, but really what ends up happening is that we have this base material proration factor that increases obviously with it keeps changing with our weld size. And so instead of, because we do have some additional capacity for our plate here, looking at some of our flange plate information, I'm going to actually go ahead and change the thickness of our plate down from a 3/4 or 3/8 of an inch, excuse me, and I'm going to go ahead and rerun that particular connection. And so we can see now that we pass, just barely, but we pass, and that really is all a result of that effective weld length. And so that effective weld length includes that thickness of the plate. And so we moved from now we have an effective weld length of that 3.53 inches, whereas before we had that effective weld length of 2.94 inches. So that gives us a greater weld strength overall at that flange weld plate to the column. So at that location where, if we look at our front view here, this is this flange weld strength here. So we've got that column to plate weld that's now passing. Now, in addition to that, we can see here that we've got some issues with HSS local plate yielding. Now, the question is, with any type, connections, we've got a bunch of connections and we can do some different things. Connections really can be designed in a variety of different ways, right? It's not like a piece of steel where you just put in the steel and then you're going to do it an optimization based on weight or, based on the moment of inertia or the section modulus or whatever. There's not just one way to design a particular connection. And so in this particular case, there's a variety of ways to kind of solve this problem, right? We can see here, in the equation, obviously we could increase the column face width. We could increase the column wall thickness. We can do some different things with the plate, right? We can increase the plate width or the yield stress of the plate. We could increase all of those things to kind of get at an additional capacity that we need. Now, in this particular case, changing our plate strength doesn't really solve our issue. So really when it comes down to it, we need to make a change to the column. Now, one of the things that you'll see here is that we're kind of locked out from changing the column, right? Because the column is being kind of governed, being driven by the RISA 3D model, we're kind of locked into that particular column size in this case. Now, one of the ways that we can go around this is we could obviously go back to RISA 3D and make those changes to the columns, or we could actually do what we'll do in this case, which is we can use the detach button. Basically, we can detach the model from the superstructure in order to have full control over the parameters of the connection. And so this may be useful when, say, you've got maybe one engineer working on the superstructure model and then maybe a junior engineer or someone else working on the connections. And so that way that the engineer can continue to work on the superstructure without maybe affecting the connections model, because you've now gotten to the point where, hey, the connections model is ready to go. We've kind of gotten to the point where that connection engineer is going to be working maybe with the fabricator, and we want to have him be as flexible as possible when he's working back and forth with the fabricator. And so I'm going to go ahead and detach this. And I'm going to go ahead and just click yes. So now let's go ahead and I'll select that connection again here. So I'll select that that connection that we were working on. So that's that similar connection we were working on here. And real quick, I'll just, I'm going to go ahead and put some of the loading information back in here based on that last issue that we're looking at. And so we're kind of back now to this HSS local plate yielding of the moment plates. And so with this, now we can go ahead and start to make some changes for our connection here. And so if we go ahead and make those changes, we can go ahead and see that we can start to make those updates. And so if I go ahead and choose to change, let's say we're going to change the connection size to start. So I'm going to go ahead down here to the column section, and I'm going to open up the column section. We have all the different column sections that are available. And so in this case, I didn't really think about maybe some of the things that Kim had talked about, where maybe what do I have available? What does my manufacturer have available, at the shop? What can they roll? But in this case, I'm going to go ahead and choose this HSS 10 by 8 by 8. So I'm going to choose that shape and click OK. Now, we can see now that we actually now no longer have a problem, right? We increased this column wall thickness, and we're using that again. We're using that full column wall thickness because we're using 1085 steel. And so we now no longer have an issue with this local flange or local plate yielding of moment plates. Now, one of the other things here is that currently, if we look at the settings of our model, so we look at the solution of our model, we're using the 14th edition code. So we're using the 36010 code. But what happens if we want to go ahead and make some of those changes? What happens if we want to update, because now the 15th edition code is now starting to get accepted by the new 2018 IBC? What happens if we're going to go ahead and use some of that information out of the new code? So I'm going to go ahead and switch to the AISC 36016. We have some different options that are included in here within the global project settings, but I'm just going to go ahead and click OK. And so some of this we can see now. If we look at this, we can actually see some of the information that maybe that we didn't have before. So if we go ahead and look at this before, we had this, and this is the picture. I just took a screenshot of what we were looking at before. The previous edition, so the 36010 edition, was giving us a code check that, or that we had to use a code check, do a limit state for local plate yielding of the moment plates and also transverse punching shear. Now you can see here, if I minimize this here, we have some additional checks that we need to do, right? So we've got not only the local plate yielding, but we've got sidewall yielding and sidewall crippling, as well as HSS column transverse plastification. So this information now needs to be included, and this is all because of the change between the 36010 and the 36016. And so if we look at this here, we're no longer using Chapter K for those things like we were before, but we're using Chapter J. So this is specification section J, design of connections. We're also using the manual chapters, Chapter 9 and also Chapter 10, and this is also included in the HSS limitations. So if we go ahead and click on these limitations, we can see here that some of the information for, say, column slenderness ratio is coming now from equations found in that Chapter 10. And so all of these things, basically, these new limit states are incorporated into RISA Connection. Now we're working with the Steel Tube Institute. Kim showed that really large spreadsheet, that compatibility spreadsheet, if you will, that showed the differences between 36010 and 36016. We're working with the STI to make sure, to just ensure that all of the changes that they've been working really hard at, they've been working with a bunch of different engineers, and as well as the AISC, to just make sure that those changes are incorporated. And so while we've incorporated the full AISC 15th edition, we certainly want to make sure that anything that they've added or tweaked that we include in our software, because we want it to be as accurate as possible for not only for any design, but for HSS connection design. Now, the last thing I wanted to mention before we go ahead and maybe open it up a little bit for some questions is, you've got all this information, you've done all this design, especially with some of the new connection design for HSS. You may need to document this in a certain way to either a code official or to a building owner or another engineer or even a connection designer, maybe from a fabricator, to just verify that you're doing what the new code prescribes. And so the way we can do that is through the printing of our reports. And so if I come up here into the print report button, I can see the report printing options that we have here. And so in this particular case, we can choose, kind of what we want to include. I'm just going to go ahead and we can include a variety of different connections. In this case, I'm just going to include one of the connections. I'm going to include all the 2D views. I'm also going to include, this is one of my favorite options, include the limit state report as seen. So maybe in this case, I've expanded all the HSS kind of limit states, and I want to see those limit states specifically included, not just kind of the available capacity, the capacity that, or the total applied load, and then the unity check. I want to see all of the information from that particular check. Now we can also include other information. So if you wanted to bring in, your details or something like that, we can do that in additional PDFs. That's no problem. And so in this particular case, I'm going to go ahead and click the Generate Report button. So I'm going to go ahead and click on Generate Report. And it's just going to bring up, obviously, our printing. I'm going to choose Bluebeam PDF because that's what I use. And Bluebeam is also a sister company of RISA within the Nemetschek group. And so we'll generate the report. It should just give us then the option to save this report, hopefully. So I'm going to go ahead and I'll just save it on the desktop here. So I'll just say Connection Report, click Save. And then this should go ahead and process the entire report and staple all the pages together and then give us the ability here, if I go full screen and we zoom in a bit, give us the ability to kind of look at our report. So if we go to the top page here, we can see kind of the general parameters as well as kind of our views, so our side view and our front view and our top view, so all the views that we created. Additionally, we can see then the the expanded views of all the connections that we've wanted to be expanded, right? So we can see all the different information for all those HSS details that we needed. And so really allowing us to document exactly what we need and want to document here in this particular report. And again, this is really just the value here is being able to show exactly what the software is doing, so there's no kind of feeling of black box, but also show, hey, here are the changes that are in the new code, and we're implementing those changes, and you're incorporating those changes into your designs. So with that, we're going to go ahead and I know Kim and Debbie as well have been answering some questions. So there may be a few questions. So if you have additional questions, please feel free to ask those in the question and answer box. We can go ahead and spend some time here. We're about 2:52 Eastern time where I am. So we can certainly stay and leave the question section open for a little bit longer. But if there's any questions, please go ahead and ask them. One question that we have seen come across that I did want to make sure I answered kind of just aloud for everybody. We do offer full demos of RISA Connection. So if you are interested in looking for RISA Connection and kind of trying it out, if you just go to our website, risa.com, and click on the products page, you'll be able to select the demo for any number of the products that you wish. You can choose RISA Connection. And so the demo is a full demo. It has access to all the different connection types that we showed here and even some of the connection types that we didn't. So everything that's available. There are some limitations just in the weld strength and the steel strength that we use, really just so you can't produce full-blown jobs with the software, but you can try out everything that you need, and you can certainly use it to ask us some questions. Let's see, we have a few questions here. One asked about kind of the round tripping, the integration here with RISA 3D again. So after you extract a model, so after we extract a model from RISA, or detach, I think was the question, after we detach a model from RISA 3D, we've basically broken that link with RISA 3D, so we can't send it back to RISA 3D at that point. So that essentially breaks the link, and it allows us to, kind of fully play with the loads and the different pieces of the model. That's why we lost our groups in that case, because we're no longer tied to that RISA 3D model. We are also able to use ASD or LRFD. You can just choose the ASD or LRFD. I was using LRFD. That's what I was raised on. That's what I've always designed. And so we can choose to use ASD or LRFD for any of the codes that we have available. One thing I didn't mention is there's also seismic provisions for 34110 incorporated with RISA Connection. So you can define in RISA 3D or in RISA Connection seismic connections, seismic brace frame connections and moment frame connections and such, and do some seismic detailing in that fashion with those connection types. And so if you need more information about the types of seismic checks or the types of seismic connections that are included in RISA Connection, again, you can visit our website, risa.com, and click on the RISA Connection product page, or you can send a question into support@risa.com. We can answer those questions for you. So we'll go ahead and leave the webinar open for a few more minutes. We'll go ahead and answer some of the questions here in the question and answer. We'll go ahead and type some of the answers out. But again, thank you for attending. If you have any other questions, either feel free to put them in the question and answer session or go ahead and email us directly. Just some housekeeping things. Your PDH certificates will be emailed out after we kind of download all the information and get it set into our system. So you'll get those. The PDH will be sent to the webinar that or the registration email. So that will come out. We'll also go ahead and post and send out the slides for today's presentation. So you can use those to validate that. If you need anything else, please email us either at support@risa.com or info@risa.com. And then, I don't know, Kim, is there a way that if they have really specific HSS kind of questions that they can contact the Steel Tube Institute?
Yes, absolutely. On the steeltubeinstitute.org website, there's a contact us page that you can get me through that.
Awesome. Thanks very much. Well, like I said, we'll answer a few more questions in the chat box, but if there's anything else, please feel free to ask that. And otherwise, thank you for attending today's webinar, and we look forward to seeing you in the next webinar in our RISA Connection webinar series. Thanks very much.